Hello, everyone. Welcome to OpenHW TV. My name is Michael Thompson. I am the Director of Engineering of the Verification Task Group here at the OpenHW Group. And for those of you who haven't been part of OpenHW TV for a while, or even those of you who have watched multiple episodes, you'll know that we haven't had a verification talk in a few months. And I'm very excited today to introduce Simon Davidmann of Imperas Software. Imperas is a founding member of the OpenHW Group, and he is now chair of the OpenHW Verification Group Task Group, overseeing OpenHW. As part of that, the Verification Task Group has started a new project to help lead develop our internal verification flows in the CORE-VERIF environment, and also to help lead the industrial adoption of RISC-V processor cores. So Simon will be joined by Peter Lewin, who is with Imagination, and Rupert Baines of Codicip, and they'll be talking about three of a set of very interesting initiatives that are happening within the OpenHW Group to address these two issues, improving the quality of our verification environment and also increasing the adoption of RISC-V cores in industry. And with that, I will let Simon Davidmann take over. Just a reminder that these are pre-recorded sessions. The pre-recording lasts for about 30 minutes. And then myself, Simon, and Peter will be available live at the end of that pre-recording session to take your questions. And with that, I will hand it over to Simon Davidmann.
Great. Thanks, Mike, for that introduction. So what I'm going to do today is, in this TV episode for OpenHW, is to talk about advancing RISC-V processor verification. And really, it's sort of an introduction to several of the projects that we've been instigating as me becoming chair of the Verification Task Group. So I'm going to give a bit of an introduction. I'm going to talk a little bit about why RISC-V verification is important. And I have a couple of guest speakers that are going to come and say a few minutes in that. And then talk about the new projects, the Advanced RISC-V Verification Methodology projects. It's not a discussion about specific CORE-V cores of OpenHW. If you want to be involved with that, join the core verification projects, look in the calendar, or come to the next VTG meeting, which is actually 21st of November. So a little bit of history here. So OpenHW started really 2019 with open source cores, with focusing on open source cores with commercial verification. Commercial industrial quality was the idea. And it was also to provide verification environments so that users could validate and revalidate their cores as well, and also use that verification environment with other cores. And the focus in OpenHW back 2-3 years ago was really the cores, of course, but also promoting the open source concept of for hardware verification, which we're going to be talking about, and also software and hardware, and more than just the chips, with the software and hardware as well. Now, we move forward now in OpenHW to October 22, where we are. Yes, it's the cores. Yes, it's the concept of open source hardware. Yes, it's verification. Yes, it's software. But also there's other areas. There's more research going on, research collaborations with OpenHW and other groups. There's prototyping with boards, MCUs, and there's also Asia and European working groups involved now with this. And what we're going to do now in this talk is really talk about verification. When VTG started, as I said, focusing on commercial industrial quality test benches, the test bench system Verilog, the system Verilog functional coverage. We used the Imperas OVP sim as a reference model, and the core was the 40P. It came and was derived from the RISC-V from E08 Zurich, the pulp core there, and then the Google's generator RISC-V DV was used in that, also with direct test and compliance tests. That was driven by Steve Richmond of Scilabs and Mike Thompson from OpenHW, and the result was really great progress, with the 40P being frozen in December 2020. So, about a year on that. And if we look at where we are now in October 22, there's 1, 2, 3, 4, 5 cores that are being developed and being verified in there. And we have the third generation of CORE-VERIF, which is just coming online, which is full UVM, full system Verilog in there. It uses an evolution of the Imperas technologies, Imperas DV, which includes verification IP as well as the reference model in there. And it provides asynchronous lockstep methodology and also the generator as before. So it's been evolving to focus on the cores. So now, after that introduction, what I want to do is talk about verification and how we see it as important. So, in terms of the RISC-V ecosystem, there are sort of 4 areas. There's the ISA itself, obviously driven by RISC-V International. There's the hardware, or we're talking about open hardware here. There's the verification methods and tooling, and then there's the software. And actually, the existing ecosystems support RISC-V very well in terms of software, tools, and chip designs, and that sort of thing. But actually, the problem that RISC-V has that we see is the verification. And if we look at the challenges that RISC-V being verification, yes, it's an open standard, and it means there needs more things need to be done. It's not just something where you're licensing in a piece of technology and it works. There's new adopters working on custom processes for the first time, where they're designing features, and really there's a lot of verification to be done related to that. And there's a lot of different methods that are being used in industry for verification of blocks, but the process of verification methods that have been used, they really are proprietary and have been used in-house by proprietary processor vendors. So there isn't established norms in how to do verification processes. And RISC-V adoption could stall with chaos if there isn't high quality compliance and high quality verification out there. And there's a lot of investment in hardware design, but actually there's a lot in software. And actually RISC-V, the Achilles heel of that is actually verification in there, because as you have an open standard, pretty much everybody can design it slightly differently. And the challenge is how you can get compliance in that. And so you've got to get compatibility across the industry. And that would really, if that's successful with that compatibility, and there isn't fragmentation, there'll be great investment and adoption of RISC-V. And one of the challenges that people are used to is that mainstream chips with mainstream processors, extremely high quality, and a lot of commercial tools have been used to get them to that. And the challenge that we have today for RISC-V in design verification is a lot of the infrastructure is actually a work in progress. And what we see is for RISC-V that verification has been evolving into sort of part of the EDA industry for some 20, 30 years. But RISC-V represents the biggest shift in verification responsibility that there has been. And then is this whole new verification ecosystem that we believe is being required in there. And without collaboration with RISC-V, there's going to be a huge problem and a lot of chaos out there. And actually, all previous open source processes have failed. ISIS have failed. Yeah, they were many years ago, but they weren't successful. They were moderately successful in the beginning, but they failed ultimately. And we don't want that for RISC-V. We want RISC-V to become absolutely the cornerstone of the future of computing here. And what we need is industry working together to develop much more efficient ways of doing things. And what we don't need is incompatible cores, proprietary incompatible verification, proprietary incompatible methodologies, and proprietary incompatible interfaces. So that would be terribly inefficient if we do that, and would cause real problems in the RISC-V ecosystem. And why do we need to worry about this now? Why is it so urgent? Well, RISC-V really adoption, I think, is at an inflection point. It's changing. Yeah, it's been around 5 years coming out of Berkeley, and then 5 years getting into industry. And now it really is at the early stages. There are not a lot of big application processes out there. They're just being developed and going to be coming on stream. Most things are in the embedded space. And we haven't really gone into volume adoption of it. And a lot of the times that the designs that are being done are sort of insulated from a lot of the issues because they're really internal processes hidden away inside a processor in one company. And the challenge is when things have to be compatible out in the industry. And what we've got to do to get this real mainstream adoption is we've got to have a high quality IP from a broad range of different people. We've got to get confidence in the way that the software is going to work on it. And we need to help people get their time to market and time to volume. And there's a lot of experience in doing that with traditional existing processes. We've got to help that in the RISC-V industry. So enough of me talking about why I think verification is important. Let's hear some of the industry people as well. I've got two talks here lined up, one from CODESIP, one from Imagination. And really, what we're sort of saying is, okay, so why is verification so important? And the first speaker is Rupert Baines, who's the Chief Marketing Officer in CODESIP.
Good afternoon, Simon. Thank you for that. It's a very important question. So just to start with, people think of RISC-V as open source, and that's a bit of a confusion. RISC-V is really an open standard, like GSM or Wi-Fi. And that means different people can develop it, and we can have interoperability and an ecosystem, which is incredibly powerful and wonderful. But it doesn't necessarily mean that everything is of the same quality. So there are commercial companies like CODESIP. We develop our own RISC-V cores. We're very proud of them. But there is also the open source community. And getting quality and verification from an open source core is something new. And that is the challenge that OpenHW Group is taking on. And I think that's going to be hugely important and hugely powerful for the industry. By having some commercial cores for people who want those, but also the option of open source products with good verification and good quality means the ecosystem gets richer and we get a positive spiral. People using those cores because they're confident they will work means there are more developers, there's more software, there's more tools, and that makes the whole RISC-V community better and stronger, which includes commercial vendors like CODESIP.
Great, thank you there, Rupert, for that. So that's a summary of what Rupert said there. It's about commercial cores and open source all need high quality, and that's obviously why verification is very important in there. So now let's also have a view from Imagination Technologies. Imagination joined OpenHW a year or so ago, and actually the chief engineer sits on the OpenHW board of directors. But we're going to hear from Pete Lewin, who looks after the CPU ecosystems. Pete.
Thanks, Simon, and hello, everyone. I'm Pete Lewin, and I look after the development of the ecosystem around our RISC-V CPUs at Imagination Technologies. Many of you may know Imagination as the leading supplier of GPU IP for mobile and automotive markets. However, at last year's RISC-V Summit, we also announced a Catapult range of RISC-V CPUs. We've already been using RISC-V for cores embedded within our GPUs for quite some time now, but the introduction of the Catapult range vastly increases the amount of RISC-V design and verification effort we deploy as we expand our RISC-V based CPU portfolio. The quality of verification for these IPs is, of course, critically important. And I believe that developing a strong collaborative ecosystem specifically around RISC-V verification will not only improve efficiency through reuse, but also contribute to increased quality through sharing of knowledge and experience. In my opinion, the OpenHW Verification Task Group and its Advanced RISC-V Verification Methodology project are key initiatives in helping drive this forward, developing methodologies that can be applied not only to the OpenHW Core-V CPUs, but to lots of other RISC-V designs as well.
Great. Thanks very much for that, Pete. That's a good lead into the projects that we're talking about here in OpenHW in the verification group, focusing on advanced verification methodology for RISC-V processors. And, in terms of a high level, what is the purpose of this project as a new project in OpenHW? Well, it's really to enhance the capabilities and efficiencies in RISC-V verification and to improve the quality of the RISC-V cores. And, verification is becoming harder and harder as implementations are getting more and more complex. And the idea is that we've got to look at new methodologies and continually improve those to be able to address the challenges that these new cores are providing. So it's about improving quality for RISC-V cores by developing better methodologies and better tooling to help these implementations be verified. When we sort of proposed this project a while back, we came up with 7 or 8 different sort of sub-projects within it. which cover things from sort of methodologies, education, standards, all the way through to SoC integration, helping work out the technologies and the tooling and the methodologies to help people integrate their RISC-V processes once they've developed them. But in this talk today, we're really going to focus on three of these: the standards, the functional coverage, and the test bench quality. So now we're going to go in and talk about the first one of these, the Advanced RISC-V Verification Methodology Project on standards. Now, the first sort of experience in open hardware on using CORE-VERIF in the sort of test bench idea really had three components in it. It had the test bench, it had the design under test, and the reference model. And then an EVM test bench was built with system Verilog to verify this. And there are really two main interfaces in here: the interface between the core and the test bench through a tracer, and the test bench connecting to a reference model. And sort of conceptually, you can think of it as sort of a little box like this, where you have the tracer coming out of the core, talking to the test bench, which talks to a controller that talks into some form of reference model in here. So conceptually, it looks like that, and that's what was developed for the initial test bench for the 40p. And if we look at RISC-V, this is off the Open Hardware roadmap slide of the website. There's a lot of cores coming on stream, being verified. There's lots of challenges related to them, different things that they have, and they all need verification to some extent. So, what are we going to do? And we've got to try and build a tracer and an interface to a test bench that sits around a core and talks to a reference model in there, when there's one or two or three or four or five or however many of these there are. Each one of them is a different core. It's going to need different things in the reference model, different things in the test bench. And are we really going to build sort of bespoke ad hoc test benches and interface for each core and each reference model to do this? Of course, no, we can't do that. That's why we need standards. We need standards which will allow us to be efficient in what we do here. And, there are many blocks that are required. They're all going to have different interfaces, requirements in there, and these interfaces need defining. And they're going to come normally from different developers, different suppliers, different teams are going to be needing these things to interconnect, and then they're going to be used in different projects with different configurations. So that's why we need these interface standards. And the goals of these developing standards is about reuse, to do things in common ways so it's easy to understand, to be able to use them quickly and efficiently. So there's a lot of goals for developing standards, and it's about interconnecting things. So we've been working since we started in Open Hardware 2-3 years ago on interconnecting things. And this has sort of evolved now into what we call the RISC-V verification interface. And it's up on a GitHub, which really has three parts to it. The trace side, which connects to the core, to the tracer, into the test bench. The API side that connects from the test bench into a reference model. And then the virtual verification peripherals area, and that allows you to have test bench components which have standard interfaces into the test bench and into the cores. And that's a work in progress part of this. But I'm now going to talk about the two interfaces that are quite well defined and in use. And these are defined in System Verilog and C, and are in use with several different main EDA simulators today. And so that's RVVI we're talking about. And you say, okay, so why RVVI? Why should we think about this? Well, you've got to use some interfaces, and there's actually no need to reinvent your own, because they don't really need to be proprietary in there, because you actually don't want them to be proprietary, and then you can reuse other blocks from elsewhere and things like that. And RVVI is really an open standard. It's up on GitHub. It's not proprietary. And it's already been flushed out in use in several different projects with several different components in there. And, actually, when you get to understand RVVI and the sort of tracer side, it helps you understand what you actually need to develop. And really, there's no real downside in adoption, but just upside to it, because it does save you a lot of development yourself. And potentially, you can use other tools and benefit from the experience of other people, because it's evolved over time with experience from different areas. And there are several tools that can make use of this RVVI. obviously we've been using it to encapsulate reference models and some verification IP in the test bench. We're now, as we're going to hear, talking about evolving and using it with functional coverage and log file writers and things like that. So there's some good questions about why it's needed. And in terms of the status today, the 40X, OpenHW is already using RVVI today, and the 40PV2, the S, and the E20 already have the use of it under development in their roadmaps, and we're starting to get it up and stream to use it. And several public statements from commercial companies, for example, Codicip says it's an essential framework, and guidelines to help configure test benches and everything. NSI Techs talks about improved efficiency and improving time to market in there. MIPS sees it as a solid foundation for all RISC-V adopters. And Valtrix, which is a test generation company, sees it providing flexibility and efficiency as they're evolving new technologies in there. So it's starting to get industry adoption outside of these sort of initial people using it in there. Now, okay, so let's talk about the actual project in OpenHW. So the initial roadmap and focus really was for the components and test bench interfaces for the components, such as the loggers and scoreboards and things, and the tracer connecting from the processor cores into the test bench, and also to control the reference model. And we're going to be talking about the connection to functional coverage in a minute. And the goal really is to make simulation-based processor verification more efficient by providing this open standard so the verification components can be used and reused more efficiently in there. So that's the sort of the focus of that of the standards project in there. And if we look at the next project in this, the functional coverage, which is about how to make it easier to do verification again. So the background is that, in verification, most methodologies, DB methodologies, should start or do start with a verification plan of what's needed. And that's going to include thousands of specific items that need to be tested. And functional coverage is a mechanism that's been used now for over 20 years in chip design, is as a mechanism to measure what is actually being tested in there. System Verilog has key concepts in it in the language which allow in a test bench to measure and count things into bins and have groups that can bring these related points together and measure at sampling times and things. And the simulators perform this counting and reporting. So as a DV engineer, one specifies these, and the simulator then does the measuring and counting and reporting for you. So it's a key, functional coverage is a key tool in the DV engineer's toolbox. And for a processor, there are several different types of functional coverage that are required. There's the standard sort of ISA architectural features, and then there's a specific core and microarchitectural features. From an ISA architectural point of view, the unprivileged things are things like the instructions and their operands, and these are standard and should be exactly the same for all RISC-V processors. When it comes to other parts of the instructions architecture for a processor like the privilege items, then there's more flexibility. There's choices that you can make, whether you have a certain number of interrupts or the debug stuff and everything. So it gets a little more complex. And actually, one of the great things about RISC-V is that you can extend it with your own instructions and register state and everything. And these become very customer specific and proprietary because they're related to the microarchitecture. And yeah, you need functional coverage for all of this. You need to measure all of this to know how much of the design your tests have actually stimulated. And if we just look at some of this, just to put it in context, RISC-V instructions, just counting up this is about 6 months ago, I think we did this, that there's almost 1,000 instructions in the basic instruction sets that have been defined. That includes the DSP, which is currently undergoing revision, but there's an awful lot of instructions in there. And for every instruction, you're going to need to write some system Verilog. Maybe, for simple sort of compliance level coverage, you need 10 to 40 lines. So you're up to sort of 40,000 lines of code if you're doing a big design. And that's not the design specific stuff. This is specific to your core. So there's an awful lot of work that needs to be done just around the standard ISA in there. And what you'll end up doing is doing it in separate sort of blocks and sections for different extensions that you're including in your design, and you'll write a lot of system Verilog that's needed for the different ISA extensions. And this is just for the unprivileged stuff, and then there's all the privileged stuff as well. So there's an awful lot of system Verilog coding that you need in terms of the verification side of things. And writing in Verilog, very tedious and error prone to write it by hand. You have to do it for every design. It's pretty unnecessary, really, to have to redo it for all the different designs, because they're all at a base level. They're trying to be compliant, of course, normally. So they all have the same requirements on the ISA. And so there really needs to be collaboration and automation to do this. And that's really what the focus of this project is to try and enable the development of open source verification IPs, such as functional coverage. And functional coverage is the first one, that can be used for many different core configurations and implementations. And if we look at a sort of a flow of how we can try and get this generated system Verilog source, we need some form of machine readable definition of the instruction set that we can then generate this code from, where we can configure it for the core that's required, whether it's a 32-bit core or 64-bit, whether certain CSRs have been implemented or not. And so conceptually, if we have this machine readable definition of the ISA, we have some configuration options, we should be able to generate all of this system Verilog source. And that's really where we're going with this project, because if you remember a minute ago, we talked about RVVI, which has a sort of standard way of connecting to the processor's tracer. You can see down here, there's a little block where it says, okay, we've got the RVVI trace client, maybe system Verilog functional coverage. So we believe that we can then hook this system Verilog functional coverage to this tracer, so that it's all becomes standard. So all each core's got to do is define this tracer to have that interface, and they can make use of this functional coverage. And that's exactly where we're going with this, is to build this system Verilog functional coverage, which sits on top of an RVVI trace layer, so it can work with any core. So you can effectively just sort of plug in this system Verilog functional coverage, connect it to the RVVI layer, and then it should just work with your core. That's just an example of it. Of course, it writes out standard system Verilog, which should be familiar for DV engineer. You run it through your EDA company's tools. This example, Cadence, with their metric tool to show it. And you can see here the coverage that you're getting out of it. And so generates the source, gives you the coverage. You should not have to do it for every design in there. And in terms of the project status at the moment, the basic extensions are available at sort of a compliance level. We're adding more extensions and more cover groups and cover points. And there's two projects that we're actively working on in OpenHW. One is the 40p V2, which is adding a floating point unit to the core, and we're generating the functional coverage for that. And also in the 40S, it has the new ZC extension, which is just being ratified at the moment in RISC-V, which is more compact code generation. We got code definition, there's code side reduction in there. And so we're just generating that. And externally from OpenHW, we have a vector functional coverage being generated that's under review outside. And where we are at the moment with this project is trying to get input and from people and from users, potential users, of what they need from the privilege mode and more the sort of pipeline microarchitectural functional coverage. What would be useful to have as general? Yes, people will have to write their own functional coverage for their own proprietary bits, but we can hopefully cover a huge amount of the work that's needed to be done in such a way that it's so easy to generate and reuse. So that's the functional coverage project. The third project I want to talk about is the test bench quality one. And so these are the three. We talked about standards, talked about functional coverage. Now I'm just going to sort of finish this discussion on the new projects, talk about the test bench quality one. And the purpose of this project is to try and make simulation-based process verification projects more efficient by allowing people to assess the quality of the verification efforts. Because it's very hard to know whether A or B is better verified. Coverage doesn't actually just tell you, because how you have to compare it to something. Coverage just tells you what's in your tests. And so the idea of this project is that we've got several things we're trying to do. We're trying to understand the requirements and the technology that's going to be needed to enable this quantitative assessment. And we have some good ideas of this, though this project's in very early stages at the moment. But we think what we want to do of how we can assess test benches and the verification solutions, and allow us to, by testing the test benches, it allows us to see how well cores are tested, and potentially allows us to award sort of quality level achievement marks to the cores being tested, so that they can say, yes, this is tested to this level or that level in there. And the idea is to focus on commercial quality levels, both architectural compliance level and also microarchitectural level. And it's about DV. So it's trying to assess the quality of the test bench and hence then the cores under test. And the way we're going to do it is initially focus on utilizing existing public tests. So we're not generating tests, we're going to create a technology which allows you to measure the quality of your verification efforts, your test bench, so that you can publicly state that without having to provide, your tests or source or whatever. So it can be used both with open source technology, but also proprietary technology, commercial companies as well. And and where we are at the moment is we're trying to look at which areas in the ISO we should be prioritizing. We're looking at the measurement and assessment approaches and prototyping something that can actually do this measurement for us, and starting to look at different test benches and verification environments, because pretty much everybody's using a slightly different setup, and we want to be able to sort of be able to compare them effectively and say which ones are good and which ones aren't, and allow people to assess them themselves. So if you're interested in this, please contact us, because we're looking for input around the ideas that we have there. And so with that, what I want to do is just sort of wrap up really, and then we'll move to the Q&A. So if you want to get more involved with this project, please contact us at OpenHW. We have a verification task group monthly meeting that's on the 21st of November, and you can go to the OpenHW calendar to have a look at that, and it is open to non-members if you want to join that. So yeah, please do that. And we are trying to sort of promote what we're doing in terms of OpenHW, but also in RISC-V verification in general. So we did a presentation on this functional coverage generation and a DV Club webinar, which has a link there on YouTube to that. Obviously, there's this OpenHW TV episode. There's a presentation at DV Club in Europe coming up in November. And then there's a lot of content around RISC-V verification at the RISC-V Summit coming up at the end of the year. And then there are other things for next year already in play. There's a paper at DVCon in spring there. And so there's a lot going on as more and more people are getting involved in RISC-V verification to understand it. So with that, I'd just like to say thank you very much for listening. And then we're going to move to the Q&A session. Thank you.
Okay. Welcome back, everybody. We're now live, and we're going to go through a little bit of a Q&A. Before we do that, I want to just make a couple of late-breaking announcements. Simon mentioned that the Imperas DB and the RVVI are being adopted by multiple cores in the CORE-VERIF ecosystem. And I just wanted to point out that just today, the pull request to do that for the CV32 E40S was completed. So now we've got two production cores that are using that, and by the end of next week, I expect to have one, maybe two more. So we'll basically have been fully converted over to this. So I'm pretty excited about that. If you're looking for a little bit more technical information, you can reach out to any one of us at any time, or attend DVCon this coming March. There'll be a paper given by a colleague of Simon's. Her name is Amy Sutton, and she'll be basically walking you through the evolution of this and speaking about why the RVVI is a big improvement, how it really enables rapid adoption of reference models and functional coverage. And I think it's going to be a fine paper to look at. Okay, so we'll just start looking through the questions just to see what we've got. This is one that comes up a lot, and this is a bit of a softball for you, Simon. What's the difference between the RVVI, the RISC-V verification interface, and the RISC-V trace spec that has been put together by one of the RISC-V international technical working groups?
Yeah, so okay, so the RVVI specification is a definition of an interface that goes in system Verilog, that goes in between the core tracer and the verification components in the test bench. Okay, so so the RVVI is an interface defined in system Verilog that sits on top of the core and its tracer, whereas the embedded trace technology that you mentioned in the RISC-V International Working Group there is to do with RTL code that goes into your chip to get the data out, whether it's through scan or change and things like that. And now recently there was I can't remember the name of it. I think a compressed version of that, a trace in there as well, of an embedded trace. And these things are really so the RISC-V International trace spec is really for RTL that you put into your design so that when you have the silicon, you can connect it up to things for monitoring and checking and presumably debug and stuff like that. Whereas the RVVI specification is for something used in verification in your test bench effectively and your test bench components, and it wouldn't turn up in the silicon. I wouldn't have thought, if that answers your question, Mike.
Well, thanks, Simon. It answers it for me, but of course I'm a bit of an insider, and I know the answer beforehand. The one way I would look at that is, RVVI is a tracer interface that you would use for pre-silicon verification when you're asking the question, does my RTL work the way that it's supposed to? The RISC-V trace spec is something that would appear in silicon when you're trying to answer the question, does the software that I've got running on this core, which presumably has been pre-verified, is the software running on this core doing what I expect it to do? So you're really attacking two different problems. With RISC-V trace spec, you wouldn't try to answer the question, does my RTL work? But with RVVI, that is the question that we're asking.
Yeah, actually, just you reminded me. Actually, when we started a few years ago looking into this, we did follow that trace specification as it was evolving in RISC-V International, and we did look and see if it was something that we could make use of rather than reinvent the wheel. Because if that's going to be in people's RTLs, why do you need any other form of sort of tracer blob in your sort of test bench sort of layers? And what we found is that the embedded trace spec really didn't have all of the data that was wanted. I mean, traditionally, those embedded traces tend to just show you where the PC is. It doesn't give you details of everything, right? And it might tell you, okay, some GPR state or whatever. But from a DV point of view, what you get in RVVI is information on every bit of state that you need to worry about for each part and each bit of the design that you're trying to verify, which isn't at all, you wouldn't get all that information out in an embedded trace. But what's interesting is that, and it's not just the bit that has changed, like, oh, the PC is moving to this or this GPR changed. By using RVVI, you can actually check that there are no side effects and that everything is exactly as you expect, comparing to some reference. Right, so you see all the side effects, not just what you're sort of looking for, and that's why the RVVI spec has we think everything that you need to do with the state of the RTL that you would need to compare with a reference.
Excellent. Yeah, absolutely agree. Got another question that popped in here. Does it make sense to start a standardized formal verification methodology for RISC-V? So I'll take that one, and I'll answer it in two ways. First of all, yes, absolutely it does. The second part of that is that's beyond the scope of this particular discussion, but stay tuned to OpenHW TV and keep looking on CORE-VERIF. There will be some pretty exciting things that we're going to be talking about that at a future date. But the short answer is absolutely. Formal verification is a key enabler for RTL pre-silicon verification. Another one that's popped up, and I think Peter, this would go to you. In fact, it was actually, I think, directed straight at you. Your title is Director of CPU Ecosystems at Imagination. And the question is, how do you see what's going on with the OpenHW Advanced RISC-V Verification Methodologies, the ARVM as we call it? How do you see that driving the RISC-V ecosystem forward?
All right, yes. Well, I think, as I've been saying, it's really key that RISC-V is successful. That's what our roadmap depends on. And for that, one of the key features is quality. It's fine getting lots and lots of different choice through different RISC-V implementations available, but making sure there's a consistent quality across all of those, and that people know if they go for a RISC-V CPU, there's some kind of standards there in how well they've been verified and what the quality will be. I think it's just really key to the whole adoption of that in any markets, really. Imagination's involvement in helping share some of our expertise in a lot of the experience we've had in that, and then also from benefiting from this standardization, really just giving that confidence to the market, that people verifying RISC-V CPUs are doing it in a consistent and standard way. I think is really key.
Excellent. Yeah, once again, you're preaching the converted. I certainly agree with everything you said, Peter. Thanks for that. Here's another quick one for Simon. Where is the RVVI documented?
Okay, where is the RVVI documented? Actually, it was on one of my slides, and apologies if some of them are a little blurred. If I recall from memory, as I quickly scanned through, I think it was on the slide that was noted as slide 31, where there was the picture of RVVI. And it's basically, it has a GitHub under RISC-V Verification RVVI. If you search for RVVI, you'll probably find up in your browser. And that's where it's documented. And as I said, is that there are three components to it: the trace, the API, and the virtual verification peripherals. And the first two are there and well documented, the trace and the API. The virtual peripherals are not a coherent specification at the moment. There's a lot of working documents. We're still talking about it. There's, in OpenHW, as in all verification environments, they exist today, and there are the virtual peripherals in the existing OpenHW test bench things. And one of the things that's interesting, and as I'm working with the RISC-V International Compliance Architectural Test Group, now they call it the compliance group there, because one of the challenges they face is that how are we going to test things like asynchronous interrupts, which require sort of test bench sort of information like these virtual peripherals in the test bench, so that you can test for compliance of the interrupt mechanisms and everything. And there is no answer yet there in the compliance group either, nor in things like OpenHW. So it's sort of still a work in progress. And we've got a paper coming up at the summit with me as VTG and Alan Baum, who's the chair of the compliance group there, talking about this and how this is evolving. So we hope to make progress on that. But the existing two, the trace and the API, are well documented on the GitHub today.
Fantastic. Okay. Here's another question that this is a perennial question whenever I have a conversation about RISC-V verification, and it's come up before in OpenHW TV. So I know what my answer is. I actually know what Simon's answer is. So we'll give Peter a chance to chime in on this one. And it is, if I run the compliance test suite from RISC-V International, why do I need that big fancy functional coverage model?
So yeah, compliance is one thing, but correct operation in all circumstances is a completely different one. So simply executing every instruction and making sure that that does what you expect in the conditions and the circumstances it's in when you execute that instruction is good, but it's not really the complete answer at all. And so there's much more to checking that you've got these coverage in all the different kind of combinations of situations and circumstances that you might find the IP in. So it's it's a first step, and then build that into far more robust verification.
Yeah, Mike, if I could just chime in on the end of that. I mean, I think that, it's a continuum from the bottom to the top. Compliance is is absolutely necessary, but it's not sufficient. And simulation-based verification is absolutely necessary, but it too is not sufficient because it cannot cover all the data paths. So there are certain areas where you need analytical stuff like formal in there. For example, floating point, where there is so much that simulation, you don't have the lifetimes to do everything. So I think there's this continuum through compliance, through verification. And really compliance, as it's defined by RISC-V International, is about, have you read the specification and sort of understood it? It's not, will it, as Pete says, will it work in all conditions? That's what DV is, right? And also RISC-V is slightly different from a lot of other previous processors in that, if you're doing a deeply embedded design that you're only going to use yourselves and program it yourselves, then running the compliance suite will show that it's going to work with the tool chains and things like that. But if you're building an application processor that's got to run 10 different OSs and software you've never seen before, you need to know that it has absolutely got everything tested. So there's different strokes for different folks in this, and there's a continuum from compliance through verification, and compliance is absolutely necessary that tests, but it's not sufficient for full deep.
Yeah, that's a phrase that was taught to me by one of my bosses many years ago. The phrase "necessary but insufficient," and that's I definitely put compliance in that. If you can't pass compliance, well, you're not there. But if you've passed compliance, now you can actually start your verification in earnest. Okay, we've got one last question, and I think I'll actually take this one myself. It says, "Are there any example implementations of RVVI available?" Yes, there are. The ones that I know about, and the ones that are near and dear to my heart, are several cores and the CORE-VERIF test bench that are run by the OpenHW Group. So if you were to Google OpenHW Group, all one word, space GitHub, you will be confronted with a list of repositories. The CORE-VERIF has several implementations of RVVI, and the CV32E40X, the CV32E40X both support an RVVI subset, and we are working to add that to additional cores as we speak. So, have a look at GitHub. You'll be able to see the implementations. If you have any questions about it, please reach out to just about anybody at OpenHW Group. And the way to do that is to create an issue on GitHub, and we'll definitely get that. And that's all the questions we have, and I'm pretty sure we're running out of time. So maybe we'll wrap it up there. I want to thank you, Simon, for leading the charge on this. I want to thank you, Simon, for taking over as chair of the Verification Task Group. Your leadership is very appreciated, and it's great to have somebody of your stature running the task group. You'll probably keep me on my toes as well. And thank you, Peter, for attending it. Imagination's been a member of the OpenHW Group for gosh, about a year and a half now. Really appreciate working with you guys, and hope to be doing more of that in the future. And with that, I will say goodbye. Thank you for attending, and check us out at openhwgroup.org.